Hi, we are from Group 16 and my name is Owen. And our group will be presenting the photonic solutions to overcome the limitations of the marker-based human motion tracking system. The target parts of the human motion tracking system that require improvements are the infrared cameras and the markers. Currently, the human motion tracking systems requires multiple infrared cameras to capture the reflected IR ray from the markers to generate a 3D coordinate mapping according to the 2D positions of the markers that are attached on the joints of the subjects. So they are highly sensitive to the marker occlusions, detachment of the markers, and also misplacements of the markers on the subjects. Other than that, the IR systems also depends on an unobstructed line of sight and also control lighting conditions. This further increase the setup difficulties of the systems and consequently increase the cost and effectiveness of these systems and also affects the access of the patients to the system. Therefore, our main goal is to use photonics technologies to design a markerless human motion tracking systems that can have higher efficiencies and accuracies for measurements and also is cost effective to increase the patient access to the system.
Hi everyone, I'm Tokape with matching number 2200463. Now I'm going to present about the solution details on the replacement of deaf cameras. There are four technologies in the deaf cameras that can be used to overcome the stated issue. The first technology is the stereo vision technology. This technology is like binocular vision, where two IR or RGB sensors are positioned like human eyes with a small distance apart between each other. The stereo disparity will be used in this technology to measure the position difference of the targeted object after comparing the images captured by both sensors from slightly different angles. As the object is closer to the camera, the disparity is larger, the depth will be shallower, and vice versa. The second technology is direct time of flight technology. This technology measures the time taken for a pulse of the infrared light traveling from the camera to the object and back to the camera. The pulse infrared light is emitted by a laser or LED source, bouncing off the object and returning to the sensor of the camera. The time delay of the light travel to the object and reflected back to the sensor can be measured and the depth can be calculated. The third technology is the indirect time of flight technology. This technology analyzes the phase shift between the emitted and reflected infrared light. The camera emits continuous wave infrared light that is intensity modulated to the object, and the light will be reflected back to the camera, causing the phase shift between the emitted light and reflected light. The difference in timing of these waves is the phase shift between the two waves, so the depth can be calculated. The fourth technology is structural light technology. The depth cameras will project an infrared light which has a structural pattern such as dots, stripes, or grids pattern towards the object. When it hits the object, the structural pattern will distort due to the distance apart from the camera and the shape of the object. The distorted pattern that is refracted from the object will then be captured by the sensor in the depth camera, and the depth of each point in the camera can be determined. Basically, by using depth cameras, the depth of each pixel can be determined before it forms a depth map which is 3D, increasing the possibility of inferring joint locations from the depth and shape itself. So no physical markers are needed to be attached as what is done currently. So the problem of uncomfortableness and detachment of markers can be overcome. Besides, AI algorithms in the depth camera can also analyze the 3D shape and motion to detect the body parts so that the skeletal motion can be tracked over time. This can solve the occlusion of markers when the hands or legs are swung during the gait, which may probably block the capture of the markers on the certain joints, such as the hip joint and ankle
In terms
joint.
of the productivity, deep camera reduce false positive or negative as it captures rich 3D data, making them less susceptible to common infrared limitation, especially the occlusion where the markers are hidden from the side of the cameras, which translates to a more accurate patient tracking, fewer erroneous alert, and more reliable data. By reducing the need for manual checks or repositioning of cameras, the instances where patients have to retake the measurement are also minimized, thus reducing the probability of patient falls. Proactively identifying and mitigating fall risk allows hospitals to realize substantial cost savings by reducing incidents and liabilities and ultimately leads to better outcome and fewer patient readmissions. Besides the safety factors, The improved accuracy and reduced need for remeasurements directly translate to improved patient flow and throughput, and hospitals can potentially optimize staffing and maximize resource utilization, thus reduce staff overtime costs and optimize the resource allocation. To advanced technology can also significantly improve the hospital's reputation, where a hospital adopting cutting-edge technology for patient safety can differentiate itself in the competitive healthcare market. Looking ahead, this solution also opens the potential for new revenue streams in the long term, demonstrated by research that stated the possibility of 5.3% cost reduction annually through data-driven initiative, including monetizing patient-provided data with strict privacy controls. Aggregated and anonymized movement data could potentially be valuable for healthcare and technology developers, though this will certainly require careful consideration of ethical and privacy implications. What we expect from users or customers is reduced wait times, where fewer errors leads to faster patient accessing. Streamlined process and better resource management can also contribute to shorter wait times for patients. Deep cameras can also provide a high quality of care with more accurate tracking and precise 3D coordinates. As a result, the condition or improvements of patient can be accurately quantified, providing more attentive monitoring that can enhance patient outcomes. Last but not least, knowing they are being monitored by an advanced and reliable system also fosters greater secureness and confidence in patients and families. That's all from us. Thank you so much.